Now, we have seen how we can use Laplace transforms to solve initial value problems, right? So we because we have also learned how to find the Laplace transforms of derivatives. So using those results, we know how to solve the initial value problems. Now, Laplace transforms can also be used to solve linear systems. Now, linear systems means that you have a system, maybe could be a circuit or could be anything, where your motion is not described by one equation. See, what happens in differential equations or even for initial value problems is that you just have one equation. Like, for example, the dashpot system, you have mx double dash plus something, something, something equal to something, right? But sometimes what happens is that your motion is described in terms of two variables, x and y, in the sense that x is also a function of time and y is also a function of time, right? And like you have parametric curves, right? Now, the thing is that if I am describing the motion in terms of these parametric types of equations, then I won't have just one differential equation with me. I'll have two. Okay, so that means I'll have one equation in which I'll be having terms like this, and another equation will be terms like this. But one thing is very clear, that my x dash is actually nothing but dx by dt, and my y dash is nothing but dy by dt. Okay. Now, when we solve, so it's like a system of differential equations. So not just one equation, you will have system of differential equations that we are solving, or we also call it solving simultaneous differential equations. Okay, the way we solve simultaneous equations or simultaneous linear equations, in a similar manner we have simultaneous differential equations. Now, when you have to solve simultaneous differential equations, that means you are looking for x as a function of time and y as a function of time, such that they both simultaneously satisfy the given system of differential equations. Okay, so I mean the procedure is the same as you have used Laplace transforms for initial value problems. We'll be using Laplace transform for both this equation as well as this equation. Okay, and then we'll be solving it. Like, for example, say supposing you have the system given as 2x double dash equal to minus 6x plus 2y, and the other system is y double dash equal to 2x minus 2y plus 40 sine 3t. Okay, so it's assumed that x is also a function of time and y is also a function of time. Okay, y is also a function of time. But since by using Laplace transforms, we can solve only initial value problems, so even when we are solving a system of equations, we need initial values for both x at 0, y at 0. Similarly, x dash at 0, y dash at 0. What are their values and so forth. So supposing we are given that for this system, they're all 0. Okay, x at 0, y at 0, x dash at 0, y dash at 0, they're all 0. Okay, now we have to solve it. Now, again, as I said, the procedure remained the same. We'll have to define the Laplace transform of xt as xs, and we'll assume that the Laplace transform of yt is ys. Okay, so using, it's like now you have two different equations with you, but they have to be solved simultaneously. So the way we have learned how to find the Laplace of derivatives, so we can write the Laplace of x dash t, though it's not required, but then we also can write the Laplace of x double dash t. Similarly, Laplace of y dash t and Laplace of y double dash t. We can write it, right? See, the purpose is again the same. We'll be converting these two simultaneous differential equations into two simultaneous algebraic equations, and then we'll be solving them separately for capital X and capital Y, or which will ultimately give us small x and small y. Is that clear? Okay, so like this will be nothing but s square xs, and this will be nothing but s square ys, because of these initial conditions that they are all 0. Okay. Now, when you substitute in your differential equation, it will be something like twice Laplace of x double dash t. Now you can write this. This was the equation, is equal to minus 6 Laplace of xt plus 2 Laplace of yt. If we take the Laplace transform on both the given differential equations, the second will give us the Laplace of y double dash t equal to twice the Laplace of xt minus twice the Laplace of yt plus 40 times the Laplace of sine 3t, right? So this implies, now what is Laplace of x double dash t? It's going to be twice of s square xs equal to minus 6. What was the Laplace transform of xt? Capital Xs plus twice of capital Ys. Is that clear? Similarly, the second equation will now become s square ys equal to twice xs minus twice ys plus, what is Laplace transform of sine 3t? Hmm?
3 upon s square plus 9.
3 upon s square plus 9. Okay. So basically now, can you not separate out, I mean, your, can you not collect, like in the first equation, I can collect the coefficients for xs. Now this is 2, so this will be simply s square plus 3 minus ys equal to 0. ये हो जाएगी ना? And the second will be minus 2xs, है ना? Plus s square plus 2ys equal to 120 upon s square plus 9. Now, isn't it like solving two simultaneous equations in capital X and capital Y? Right? So, what we can do is we can solve them further and we'll get xs equal to something and ys equal to something. Is that right? Can you quickly solve it and see what do we get? It's like solving two simultaneous equations now. Use elimination, do whatever. Substitution, follow any method you want. But I want, like, what we want is the solution. Capital Xs equal to something and capital Ys equal to something. You can use any of the method of solving. I mean, you can use Cramer's rule, you can use elimination, you can use substitution, use any method. But what we want is two functions, okay? Capital Xs and capital Ys. So what do we get?
Ma'am, xs is coming 120 upon
xs is 120 upon,
S square plus 1
uh,
into S square plus 4 into S square plus 9.
that's right. And ys,
मैम वाई एस इज यही पूरा जो एक्सेस का एक्सप्रेशन है इंटू एस स्क्वायर प्लस 3.
that's right. So this is basically this upon s square plus 1 into s square plus 4 into s square plus 9. Okay, now we have to solve them back. Can you do them? Because we need xt and we need yt. कर लोगे इसको अपने आप? अब तो
Yes,
पहले
ma'am.
जैसा हो गया ना. You have to now split it into partial fractions and then use the results and get your xt's and yt's. Hmm? हो जाएगा?
Yes, ma'am.
Right. So this, I mean, this way you'll be now able to do your problems from 11 till 16. Okay. But sometimes, so I'm proceeding on with, and sometimes what happens is that, while like if you just look at your exercise and see the problems from 25 till 30. Okay. So what happens is sometimes when we have to find the Laplace transforms of functions, like in the so far what we have done is we have simply used the standard Laplace transforms. Okay, we have used them to convert differential equations into algebraic equations and then we have solved them, right? But sometimes what happens is that we have to make certain modifications. Like for example, if you just look at your uh, question number, okay, let's do this first, um, the example, and then I'll move over to, like for example, like it says we have to show that the Laplace transform of t e to the power at is equal to 1 upon s minus a square. Okay, now see what is the difference here. We know we have a standard result that, or in other words, we know the Laplace transform of e to the power at, right? But the function has changed now. Okay, but the moment I look at this function, okay, what I see here is that this is actually nothing but actually a derivative of e to the power at, not exactly derivative, but if I just use this product somewhere, see what we do in this case is whatever Laplace transform we have to find, we assume that as our function, okay, ft as t e to the power at. Okay, now if you just look at this function, it's obvious from here that f at 0 is 0. When t is 0, the function is also 0. But the moment I look at this and I try to find its derivative, f dash t, then f dash t is nothing but e to the power at plus a t e to the power at, isn't it? Right? And what happens to f dash at 0? What is f dash at 0?
1.
1, right? Now, if you see the Laplace of this, see why I'm looking at the Laplace of this, because this term involves both my standard function as well as the function that I need. Okay, so what I do is instead of directly evaluating the Laplace of this term, I'll compute the Laplace transform of f dash t. Okay, so instead of that, means what am I doing? Instead of computing the Laplace transform of ft, I'm starting with the Laplace transform of f dash t. Okay. Now, what will be that? The Laplace transform of EAT plus EAT e to the power AT. But we know the linearity property of Laplace transforms. So this will be nothing but Laplace transform of e to the power AT plus a times the Laplace transform of t e to the power AT. Okay. Now, by the theorem that we did when we found the Laplace transforms of derivatives, can you just recall what was the Laplace transform of f dash? क्या होता है? By the theorem that we did, the Laplace trans, and we used it while solving differential equations. What is the Laplace transform of the first derivative?
मैम एस एफ एस माइनस एफ जीरो.
S into
मैम एक्सेस, कैपिटल एक्सेस
so
माइनस
basically S into Laplace transform of ft. यही हुआ ना?
फंक्शन
माइनस
हाँ,
एफ जीरो.
minus
एक्स
f0.
एफ
यही
एट
होता है?
जीरो.
Is that right?
यस मैम.
यस मैम.
Right. Now, if I just look at my function here, what is f at 0? 0. So that means for all such functions where the function vanishes at 0, basically your Laplace transform of f dash t is nothing but s times the Laplace of ft. ठीक है ना? But what was the Laplace of ft? What is ft in this case? ft in this case was this function. ठीक है ना? So this is nothing but s times Laplace transform of t e to the power at. Now, if you substitute the things back in this equation, what do you get? Your left, that means your left hand side is s times the Laplace transform of t e to the power at is equal to, what was the first term? Laplace transform of e at. यही है ना? Plus, what is the second term? A into Laplace transform of t e to the power at. Now, this is something that we wanted to compute. We have two terms like this, so we can always combine them. So I have s minus a Laplace transform of t e to the power at is equal to Laplace transform of e to the power at. And what is the Laplace transform of e to the power at?
1 upon s minus a.
1 upon s minus a. So this implies Laplace transform of t e to the power at is nothing but 1 upon s minus a square. This is what we had to prove. Okay. So what I wanted to convey here is that sometimes we can use, we don't use directly the function itself to find the derivatives, but we start with the Laplace of their derivatives and then we find the things like this is how the next example, you can try it yourself. You can find the Laplace transform of t sine kt. Okay, so what we do is we start with this as ft, and this method helps in all those functions where f at 0 is 0. Okay, and you can see from here f at 0 is 0. So when you find f dash t, f dash t will be nothing but sine kt, है ना, plus kt cos kt. यही हो जाएगा ना? Now see, why I have taken up this, because this is a trigonometric function. Now, in the earlier case, just the first derivative itself had given you the terms in which this term was also present. मतलब जिसका हमें लाप्लास ट्रांसफॉर्म निकालना था. वो भी प्रेजेंट था उसमें, ठीक है ना. बट इन दिस केस इट इज नॉट द केस, राइट. दो आई हैव दिस, and if I have to find the Laplace transform of this, I can always find it. It's not a big deal, okay. But what happens to f dash at 0? How much?
It
What
will
is
be
it?
0.
Again 0. Okay. So the moment I have this, it gives me an idea. Why not find f double dash t? Because I know that if I differentiate again, this cos kt will have the derivative as sine kt, which is required actually, right? So what will be f double dash t in this case? F double dash t will be k cos kt. Not a big deal because there is no t with cos kt, right? The second term will be plus k cos kt minus k square t sine kt. Am I right? So which is nothing but 2k cos kt minus k square t sine kt. Right? Now I've got what I wanted. Right? So if you take the Laplace transforms on both the sides, your equation now gets reduced to Laplace of f double dash t is equal to, what was the first term? 2k Laplace of cos kt minus k square Laplace of t sine kt. Is that so? But what is the Laplace of second derivatives? क्या होता है? S square Laplace of ft, यही होता है ना? Minus s f dash and so on, but both of them are 0. F dash at 0 is also 0 and f at 0 is also 0. So we won't get any more terms, right? So that means this is equal to whatever right hand side we have. But what was Laplace of ft? This implies you have s square Laplace of t sine kt is equal to 2k Laplace of cos kt minus k square Laplace of t sine kt. So again, you can combine these two, you know the Laplace of cos kt, and you get your result. Things become very simpler here. Okay. Similarly, like if you just look at your question number 25, 26, 28, 29, 30, they're all similar to this. Like if you just see your question number 25, you have to derive. Now see this in question number 25, we have to derive the formula for sine kt. This we know. Sine kt का हमें पता है, Laplace transform of sine kt we know. But then the problem says you have to now apply that result of the derivatives, Laplace transform of derivatives, from the formula of Laplace transform of cos kt. Okay. So that means we have to use this to derive the formula for sine kt. Is the question clear? Huh? Just let me know.
Ma'am, please repeat it.
The problem says apply theorem 1 to derive Laplace transform of sine kt from the formula of Laplace transform of cos kt. See, these are two standard functions for which we have already derived the formula. But then those formulae that we derived were by using the definition of Laplace transforms. हमने इंटीग्रल से निकाले थे ना, right? But now, since we know the theorem which talks of the Laplace transforms of derivatives, like Laplace transform of f dash, Laplace transform of f double dash, and so on and so forth. And we know that there is a relationship between the derivatives of sine and cos. Similarly, there is a relationship between the derivatives of sine hyperbolic and cos hyperbolic. So these functions typically can be derived from each other, you know. So we can use the formula for Laplace transform of cos kt to derive the formula for Laplace transform of sine kt also. So that means in this case, we'll assume our ft to be cos kt. Okay. So what will be f dash t? F dash t will be minus k sine kt. Right. Now, if ft is cos kt, we know we have to use the formula for cos kt. Now, what is the Laplace transform of cos kt?
K upon S square. S upon S square plus K square.
S upon s square plus k square. Right? Now, see, if f dash t is this, then what will be the Laplace transform of f dash t? It will be minus k Laplace transform of sin kt. ठीक है, और यही हमें निकालना है एक्चुअली, है ना? That means Laplace transform of sin kt is minus sorry, if I'll now use the derivative, I'll now use the formula for the Laplace transforms of derivative. So that means this will also be equal to क्या होता है s times Laplace transform of ft minus f at 0, यही होगा ना? I'm writing the formula here. Is this clear? एक मिनट फिर से लिख देती हूँ. Minus k sin kt. Sorry, I'll write it again. Minus k Laplace transform of sin kt is actually equal to Laplace transform of f dash t. यहाँ तक तो कोई प्रॉब्लम नहीं है ना? But what is Laplace transform of f dash, the first derivative? It's s times the Laplace transform of the function minus the value of the function at 0. ठीक है? But what is f at 0? Your ft was cos kt. So what is f at 0 in this case?
1.
1. Okay, so that means this is nothing but s times the Laplace transform of cos kt minus 1. Is that right? But what is Laplace transform of cos kt? Because we have to use that. The problem says derive the formula for Laplace transform of sin kt by using the Laplace transform of cos kt. So how much is the Laplace transform of cos kt? अभी बताया था तुम लोगों ने क्या था? S upon s square plus k square minus 1. यही है ना? Am I right or wrong? That means minus k Laplace transform of sin kt is s square upon s square plus k square minus 1. Am I right or wrong?
Yes, I'm right.
Yes, ma'am.
Which is actually nothing but minus k square upon s square plus k square. That means Laplace transform of sin kt is minus 1 upon k into minus k square upon s square plus k square. Right or wrong?
I'm right.
Right. And which is actually nothing but
K upon S
k
square plus
upon
square.
s square plus k square, which we know is the Laplace transform of sin kt. यही होता है
Yes,
ना?
ma'am.
Right?
Yes, ma'am.
So it's just that this is, I mean, this is another way of deriving. Similarly, you can derive the other way around also. I mean, you can derive the Laplace transform for cos kt by using the Laplace transform of sin kt. Similarly, cos hyperbolic kt by using sin hyperbolic kt, because they enjoy a special kind of relationship. So we can always use them. Is this clear? But just look at question number 27. This is interesting. We just now derived the Laplace transform of t e to the power at, right? Now, we'll derive the question number 27 says, again, see, why it's always using now these problems are using theorem 1, right? What did theorem 1 talked of? Theorem 1 talked of the Laplace transform of f dash, Laplace transform of f double dash, and not just this, we can talk of the Laplace transform of the nth derivative of that function also. Okay, so that means if I have a function, of course, which satisfies those basic conditions that are required, then we can talk of the Laplace transforms of any order derivative for that function, right? So that's why when just look at question number 27, it is not talking of this, but it is talking of a function like t to the power n e to the power at. Okay, so you have to prove that this Laplace transform is equal to n upon s minus a into the Laplace transform of t n minus 1 e to the power at. Okay, this is what you have to prove. Okay, this is not a big deal, right? This is still simple, but look at the second part. Okay, then using this we have to deduce something. Okay, and we have to deduce that Laplace transform of t to the power n e to the power at is actually nothing but n factorial upon s minus a to the power n plus 1 for n equal to 1, 2, and so on and so forth. Okay, which is obvious. See, if I'm able to prove this result, then I can use the same result to substitute this. Okay, that will be what? T to the power n minus 2. So again, the result can be used and so on and so forth. So you will have things like n into n minus 1, n minus 2, and so on and so forth. So you'll get n minus n factorial and s minus a repeated every time. Okay, so we'll have that. But let's see. Yeah, we can do it. I'll just give you hints and you can try it yourself also. Okay, now again, we'll start with ft as t to the power n e to the power at. So the procedure will be the same as we have done here. Okay, so what will be f dash t? N t n minus 1. This will be the first term plus a t n e to the power at. Okay. Now using this, what is f at 0? 0. What is f dash at 0? Again 0. Okay. Now see, I'll take Laplace transform in this equation. Now I'll write the right hand side first and then the left hand side because we need to use the results. Okay. Now this means Laplace transform of n t n minus 1 e a t plus a into Laplace transform of t n e to the power a t is equal to Laplace transform of f dash t. Okay, which is actually nothing but s times Laplace transform of ft minus f at 0, which is actually nothing but s times the Laplace transform of t n a t. That's it, because f at 0 is 0, right? So that means what we have is that n times the Laplace transform of t n minus 1 e a to the power t plus, what was the second term? A, right? Laplace transform of t to the power n a t, yahi hai na? Is equal to s times the Laplace transform of t n e to the power a t. Is that right?
Yes,
Now,
ma'am.
these two terms can be combined. You know? So that means n times Laplace transform of t n minus 1 at is equal to s minus a Laplace transform of t n e to the power at, which means Laplace transform of t n e to the power at is equal to n upon s minus a Laplace transform of t n minus 1 e to the power at. This is what we had to prove. Not a big deal, as I said. It's very mechanical. We just had to use the same logic here, right? Now, using this result, can we not write the Laplace transform of this? That means what are we doing? We are simply replacing n by n minus 1 here. Okay, so it will be what? N minus 1 upon n minus a Laplace transform of t n minus 2 e to the power at. यही हो जाएगा ना?
Yes, ma'am.
Similarly, again if I use, can I not find the Laplace of t n minus 2 e to the power at? That will be n minus 2 upon s minus a Laplace transform of t n minus 3 e to the power at, and so on and so forth. A stage will come when I'll have Laplace transform of t square e to the power at. That means replace n by 2, which will be this into this. And this you have already proved. What was that? 1 upon s minus a square. यही प्रूव किया था ना हमने अभी सबसे पहले.
Yes, ma'am.
Now substitute back. Substitute this value that you have obtained here. Then whatever you get, substitute in the previous, and so on and so forth. When you substitute back, you will get the answer that we were to prove. इसी तरह से आ जाएगा ना. You will get Laplace transform of, in fact, t to the power n e to the power at will actually be, what was the first term? N upon s minus a. The second will be n minus 1 upon s minus a. Then n minus 2 upon s minus a, so on. 2 upon s minus a and 1 upon s minus a square. Because of this, you will have n factorial upon s minus a to the power n plus 1. Because you'll have n such terms and plus 1 extra. So you'll have this result. Okay? So this is what we were to prove. And this can be used, to find the Laplace transforms. Is that okay? So, yeah, in fact, 28, 29, 30th also have to be done like this. So what I'll do, what I'll suggest is, you try out these problems. Okay.